the last video, we started looking at radicals, basic examples. We're going to build off of that in this video, look at more examples, and then get to radicals that deal with variables and different powers. So going back, quick review, negative square root of 81. What is that? Well, here they're saying, what's the negative root of this number? And that's negative 9. Because negative 9 times itself gives you positive 81, which is what you're looking at right here. And they're just saying here, give us that negative root. Next they say, give us the positive and negative root of 169. Well, 13 squared is 169, so or negative 13 squared will give you positive 169. Then we get to problems that for square roots that are not perfect squares. The strategy and the idea here goes back to a fundamental idea in radicals, which I discuss in other videos. It's just that the square root of a times the square root of b, or and so forth, equals the square root of a times b. And we're going to start here and work backwards. So that means that the square root of 8 is the same thing as the square root of 4 times 2, which is like a times b. And then we split it up, which equals the square root of 4 times the square root of 2. And the square root of 4 is 2. The square root of 2 is irrational, so we leave it as 2 times the square root of 2. And that's it. So next we get the square root of 162. So when you get numbers like this, here we're dealing with even numbers, so try and divide by 2 and see what happens. Here that works out nicely because this is equal to the square root of 81 times 2, which equals the square root of 81 times the square root of 2, which equals, well, the square root of 81 is 9, and that's times the square root of 2, and we're done. Next we have 3 times the square root of 200. Well, again, dividing by 2, I realized that the square root of 200 equals 2 times 100, which is a perfect square right there, which is fantastic for us. So that equals 3 times the square root of 2 times the square root of 100. Well, the square root of 2 is still irrational, so it's 3 times the square root of 2 times 10, because that's the square root of 100. And then I use the commutative property, and I'm going to multiply 10 by 3, right? And that's going to be 30 times the square root of 2. And last in this category, I'll write it right here, we have, I'll use a different color, we have 3 times the square root of, actually, let me show you one interesting thing. I'm sorry about this, about 200. I have this written down here, so I thought it was a new problem, but all I'm showing here is that when you're dealing with problems like this, you don't need to use this exact strategy. I could have said that 3 times the square root of 4 times 50 is also 200, right? This is also 200, so this still works, and that equals 3 times the square root of 4 times the square root of 50. The square root of 4 is 2, so 2 times 3 is 6 times the square root of 50. And now I just have to keep breaking this radical down. So 6 times the square root of 25 times 2. 25 is a perfect square. That equals 6 times the square root of 25 times the square root of 2, which equals 6 times, this is 5, which is 30 times the square root of 2, which is exactly what we got before. So if you're dealing with a problem where you're trying to find a root, and you're not given a perfect square root or cubic root or so forth, we can break the problems down like this. And I think that'll really help. And this leads us into some radicals with variables. And we're going to just use the patterns of what we're doing so far to figure this out. So as an example, we have the square root of 36 times a to the 4th times b to the 6th. Now, the concepts that work behind this problem are definitely explained in detail in other videos, but the patterns here are quite simple. One thing we have to remember, as a side note, I'll put it up here, x, any variable, to any power, times x to, I don't know, a different power. When we have this situation, we add up the exponents, right? So for example, x to the n times x to the m equals x to the n plus m. This is a fundamental exponential law. And as a quick example, if I have 2 squared, so 2 would be x here, times 2 to the third, that equals to 2 to the 3 plus 2. I'm adding the exponents, or 2 to the fifth. And briefly, the idea is that 2 squared equals 2 times 2, and 2 to the third equals 2 times 2 times 2. That's 1, 2, 3, 4, 5 2's being multiplied. And that's the same thing as 2 to the fifth. So with a square root, it's kind of a special case of this. If I take the square root of, let's say, x to the n, right? That's saying what base times itself gives n. So that would be 1/2 n, and then 1/2 n. Because we're going to add a half and a half, we get 1 whole n. So again, that's going to help guide us if I haven't lost or completely destroy that explanation here. That's going to help us out in this problem. So building on what we said before, we're going to break these up. And we're thinking of this as the square root of 36 times the square root of a to the fourth times the square root of b to the sixth. So square root of 36 is just 6. The square root of a to the fourth is a squared. Why? Well, again, I'm looking for the square root of a to the fourth. So I'm asking myself, what times itself will add up to 4? And it has to be the same thing. So the only number that plus itself that I know of that adds up to 4 is 2. So a squared times a to the square times a squared, you add the exponents, and that would give you a to the fourth. So really, what we can do in problems like this, especially when the exponents are even like this, we just divide them in half. So a to the fourth becomes a to the second, and then following that pattern, b to the sixth would just be b to the third. And we are in fact done now with that problem. And this can become more complicated. In the next example, you have the square root of 1.44, and then a to the fourth, b to the 16th, and c to the 36th. So here, I'm not actually going to even write it out, the different parts. I'm going to visualize that. So I'm going to think of this square root, then this, then this, then this, and that'll save me some time. So square root of 1.44 is equal to 1.2. I think of 12 squared as 144, so 1.2 times itself has to be 100 times smaller, and I went over that in the last video, so that's 1.2. A to the fourth, well, this exponent divided in half is a squared. B to the 16th, what's 16 divided by 2? That's 8, that's b to the 8th. C to the 36, well, what's 36 divided by 2? That's 18, so that's c to the 18th. And once we use that pattern established here, we can quickly solve these types of problems. Another one we have is 5 times the square root of 81 y to the third, u to the sixth, and z to the eighth. Same idea. We're gonna break these into different pieces, and we're multiplying all of that by 5. So we have 5 times 9. I'm getting that from the square root of 81. And the tricky part here is y to the third power. Typically, the way we deal with y to the third, if I just had this, would be to say, well, that's equal to y squared times y, which equals what? Well, that equals y squared is equal to the square root of y squared is just y, and the square root of y is still the square root of y. So what you do when you have an odd exponent like this, think of it as in terms of the base times to an even exponent times the base of the first power. So for example, here's y to the third plus y to the second, base to the even power, times y to the first power. So if I gave you y to the fifth power, which you can think of that as is y to the fourth times y, that's the same thing, we add those exponents, and that equals, well, the square root of y to the fourth is y squared, the square root of y is, we don't know, it's still the square root of y. And this approach can work. Why don't we just cut this in half? Well, we could. It would just be a little bit tricky to recognize what's happening, because then we would get y to the 1 and 1/2 times y to the 1 and 1/2. Oops. And then you'll be taking the square root of this. This is just less friendly to deal with, but ultimately you'll get the same thing, because you might remember that y to the 1/2, that means the square root of y. So each of these, what it's saying is take the square root of, in this case, I'm going to break that up to y times y to the 1/2, and then again over here, times y to the 1/2 times y. And now this order, these two together, and I would pair these two together, just to resimplify and think about it. So these two y's together is y squared, so we have the square root of y squared, and these two together is equal to y. So that brings us right back to here. That's second step. And I have to go through all this and eventually get the same answer of y times the square root of y. Basically, it's just a quicker way to deal with an odd exponent is to rewrite it in terms of an even exponent. Whew. So all that said, y to the third power would reduce to, well, the square root of y squared times y. I'm not going to evaluate it. I mean, I already did down here, but I'll wait. And then u to the sixth, that's u to the third. Z to the eighth, square root of that, z to the fourth. So we're almost done. 5 times 9 is 45. The square root of y squared is y, and the square root of y is still the square root of y, so we have 45 times the square root of y times u to the third. We typically cluster all these together, and I put the square root at the end, times z to the fourth times y, the square root of y. And that's how I deal with that problem right there. And in the next video, we'll deal with some more algebra problems like this and some other radicals as well. Alright, hope this helped.